Rotational motion is similar to the circular motion, but there is one big difference. So in both motions, the object is moving around the circle, but in the circular motion, the object is going to be moving around the axis of rotation that is outside of that object. So think about the ball attached by a string to whatever, to your hand, and then you're rotating, you're spinning it around. Yeah. So the axis of rotation is going to be you, and then the ball is rotating around you. With rotational motion, an object is rotating around its own, the axis of rotation goes through itself. So think about a merry-go-round or a Ferris wheel. The axis goes through the center. So we will look at this. Oh, and the object is going to be, we're looking into a rigid object, which means that it is, well, not flexible, it's rigid. So that means that the shape is going to be definite. And for simplicity, we will look at this circle. It rotates around, so circular object, some wheel, rotates around the point O, the center of the circle, in the counterclockwise direction. So all the points are rotating like so. The axis of rotation is kind of like sticking out of the page towards us or out of the screen towards us. So, and that is an imaginary line. So we need to indicate the angular position of our object and how far it is, in other words, how far it has rotated. So in order to do that, we specify our angle theta over here, of some particular line in the object, with respect to reference line, and the reference line is going to be our positive axis x, just like in trigonometry. And actually you will see that this is related to trigonometry. So positive axis x, that's the initial side. First of all, let's discuss what 1 radian is. So again, something from trigonometry. So 1 radian is when you have a radius of your circle and then you're going to put it around the arc. So you bending that radius around the arc. Then it's going to cut off the angle theta that is going to be equal 1 radian. In other words, we would say that 1 radian is the angle subtended. So there is this word subtended by an arc whose length is equal to 1 radius. Now, since we would have an angle theta that is in this diagram subtended by an arc whose length is L, okay, and the radius of the circle is r. So what we can say for this diagram is that angle theta is equal L over r. That's going to be our equation, and angle theta is in radians, right? So we're calculating in radians, not in degrees. Forget about degrees from now on, only radians. So angle theta is in radians, and that's going to be our, let's call it equation 1. All right, so, well, we know that if L is going to be equal r, the radius, you can see that you will have r over r, so theta is going to be 1 radian, what we just discussed. Now from here we can say that the distance L has to be equal r times theta. Those are equivalent equations. And we also know that if the length of the full circle is 2 pi r, and then we divide that by r, then we will have 2 pi radians, right? 2 pi radians, which is equivalent to 360 degrees, equals 360 degrees. So we can use this ratio, or better yet, use pi equals 180 degrees, so pi radians equals 180 degrees, to convert between degrees and the radians, and vice versa. And for our first example, we are going to look at the conversion. So our first example is about a bike wheel. A bike rotates 4.5 revolutions. How many radians has it rotated? So again, we are looking into 1 revolution being equal 360 degrees, which is 2 pi radians. And we know that we rotated, or the wheel rotated 4.5 revolutions. So we have to multiply 2 pi times 4.5. 4.5 revolutions multiplied by 2 pi. That is going to be 2 pi radians. That is going to be 9 pi radians. Or if we punch the buttons on the calculator, we will see that it is approximately equal 28.3 radians. 28.3 radians. That is equivalent to 4.5 revolutions. Our next example is going to be a bird of prey who is looking at some mouse down there while it's flying. So particular bird's eye can just distinguish objects that subtend an angle no smaller than 3 times 10 to the negative fourth radians. How many degrees is this? We will have to convert. And then how small an object can the bird distinguish when flying at a height of 100 meters. So this is our diagram. We can see that the bird is flying here. The object is there. This is our angle theta over here. R is going to be 100 meters, and the angle is 3 times 10 to the negative fourth radians. So let's see how we would solve this. First thing, we need to convert our radians into degrees. So that means that we are going to multiply our 3, part A, 3 times 10 to the negative fourth radians. We have to multiply it by 180 degrees and divide it by pi, or you can multiply by 360 divided by 2 pi. I already simplified it. So this is going to be approximately equal 0.017 degrees. Very, very small angle here. For part B, how small is the object? We know that L equals R times theta, right? We're already using our equation here, and we are going to multiply our 100 meters, that's the radius, and then our theta is 3 times 10 to the negative fourth. Yes, I know we just converted that into degrees, but remember the equation was only in radians, so we have to use the radians. I'm going to write down radians here. So that is going to give you 3 times 10 to the negative 2 meters, which is 3 centimeters. 3 centimeters. 3 centimeters is, it's very small. It's like a baby mouse there. So that means that the bird can distinguish a mouse down there, a baby mouse, or like a big mouse, or a rat is like no big deal. All right, now to describe rotational motion, we need to make use of angular quantities as well. For example, we will look into angular velocity and angular acceleration. Let me open up this diagram here so that we can look at the wheel. So we're going to look at this object here. An object like bicycle wheel, for example, rotates from some initial position we specified by theta 1 to another position, theta 2. So displacement, the angular displacement is going to be delta theta over here. Delta theta is theta 2 minus theta 1 equals theta 2 minus theta 1. All right, so that is the angular displacement. The angular velocity, which we for which we use letter omega. So that is angular velocity. No more letter V, so it's omega. It is defined, well, by analogy with our linear velocity. We would say that angular velocity, average angular velocity, has to be equal delta theta over delta t. So what was the rotation over some period of time? And instantaneous angular velocity is therefore going to be equal limit of our delta theta over delta t as delta t approaches 0. Right, so instantaneous at an instant. And that is going to be, so those two equations are going to be equation number 2. I'm going to say that those two are equation number 2. Right, so we know it's delta theta over delta t, or the limit of those. So angular velocity is usually specified in radians per second. Radians per second. And a very important part to mention is that all the points on the circle rotate with the same angular velocity. So it's not just the parts on the outside or the outer edge of the circle, right? It's all the points on the circle. Wherever you take the point, close to the center, far away from the center, it does not matter. We can rotate the object in a clockwise direction. That's going to be a negative rotation, or counterclockwise, that's going to be positive rotation. Same thing, just like in trigonometry, very basic stuff, trigonometric stuff. All right, now for the angular acceleration, we would have to, so we would use, for angular acceleration, we would use letter alpha. Angular acceleration. We're using letter alpha, and the average angular acceleration is going to be equal, again, similarly to the linear one, omega 2 minus omega 1 over delta t, which is delta omega over delta t. And for the instantaneous angular acceleration, we would just, very similarly to this, we would have to calculate the limit of delta omega over delta t as our change in time approaches 0. And I'm going to say that those two are equation number 3. Okay. Equation number 3. So that it's easier for me to refer back to those. So I'll say equation number 2, equation number 3. You will know what that means. All right. Because angular velocity is the same for objects, for all points on the object, that means that angular acceleration is also going to be the same for all the points, no matter where the points are. It's going to be also the same. However, now we're going to somehow tie together our linear velocity and acceleration and angular velocity and acceleration. So let's take a look at this diagram, number 8.4, this figure. So if you have a point somewhere on a disk, rotating disk, it will have at any moment an angular linear velocity, sorry, and the linear acceleration. So linear velocity is going to be tangential to the circle. We talked about it when we discussed the circular motion, so it's going to be tangential. And that means that we can say that V, the magnitude of V, or V, is going to be equal delta L over delta T. So delta L is this distance, right? So the angle, the angle was delta theta. So the wheel rotated a little bit, but since we are talking about very, very small quantities, we can say that delta L, it's a segment, it's not really an arc. So delta L over delta T. However, remember we said that L was equal r theta, so delta L has to be r times delta theta. R is the same, r doesn't change, but it's the angle that changes. So now if I plug it in here, I'm going to get V equals r delta theta over delta t. But delta theta over delta t is nothing else but the angular velocity, which means that linear velocity V is going to be equal r times omega times the angular velocity. So that is my equation number 4. And that is the equation that shows how linear velocity and the angular velocity are connected. Now, another thing that I wanted to mention is look at this diagram, 8.5. So the wheel is rotating counterclockwise, and then we have 2 points on the wheel. One is a little bit closer to the center, one is a little bit further away on the center. We know that they have the same angular velocity because they will rotate through the same angle, right? So the central angle is going to be the same. So that's angle theta. However, the linear velocities are going to be different because they will travel different distances. This distance is shorter than this distance over here, which means that V, because V equals r omega, and radius to point A is smaller than radius to point B. That means that velocity at the outer edge, velocity further away from the center, linear velocity is going to be greater than the linear velocity closer to the origin. I called it origin, to the center of rotation, to the axis of rotation. Now we will look, same thing about the acceleration. So we remember the angular acceleration is going to be related to the tangential acceleration by this equation. So tangential acceleration is linear, right? So it's v over t, or delta v over delta t, I shall say. And instead of delta v, we know that it's going to be r delta omega, right? Delta v is r delta omega over delta t. And delta omega over delta t, that is the angular acceleration. So that means that we can say that the tangential acceleration has to be equal r times alpha. And that is my equation number 5. My equation number 5. So the radius of the circle, and then ATAN, stands for the tangential acceleration. Let's take a look at our next piece here. We remember that the rotating object has also the centripetal acceleration. So that means that the total acceleration has to be equal, A has to be equal tangential acceleration, and I'm using vectors now because remember it's a vector, plus the centripetal acceleration, which we called AR, right? Radial or centripetal acceleration, which we discussed before. Remember that AR was equal v squared over r. So now we can plug that in and see that AR is going to be equal. So it equals v squared over r. Instead of v squared, I can plug in r omega squared over r, which means that I will have omega squared, and then r squared divided by r is going to cancel, and I'm going to have omega squared r. This is equation number 6. So that means that the centripetal acceleration is greater the farther you are from the axis of rotation, because if you look at this, the centripetal acceleration actually depends on the radius. So it's the farther you are from the axis of rotation. For the connection between linear and rotation quantities, we can look at this table. So in linear um, in linear movement, we have our quantities x, v, and acceleration, tangential acceleration. Rotational, similar quantities are going to be theta, so displacement is measured in angles, velocity is omega, and acceleration is alpha. And the relation is, as we said, x is going to be r times theta. We called it L in the beginning. V, velocity, linear velocity, is r omega, and then tangential acceleration is r times alpha. And remember that angle must be measured in radians. Now we have a couple more examples to look at. Our first example is about angular and linear velocities of a carousel, people moving on a carousel. Let me see, make this one visible. Okay, here we go. So carousel is a merry-go-round. Yeah, carousel is initially at rest at t equals 0. It is given a constant angular acceleration. It increases the angular velocity for 8 seconds. Now at 8 seconds, we are going to figure out the angular velocity of the carousel and the linear velocity of a child located 2.5 meters from a center. So that's point P. I did not include the picture of a merry-go-round, but this is our point P over here. All right, so for part A, let's start for part A. So our equation 3 was that alpha is delta omega over delta t. All right, and we will be able to solve for omega once we know our 8 seconds. So now with omega, we will be using our linear velocity using our equation 4. Linear velocity, v equals r omega. So that is our logic here. All right, so in our equation 3, we said that the average velocity has to be delta omega over delta t. So we can say that, or omega 2 minus omega 1 over delta t. We know that delta t is 8 seconds. We know the average acceleration was this one, 0.06 radian per second squared. And omega 1 was equal 0 because the carousel initially was at rest. So let's plug in the numbers. So we have 0.06 radians per second squared equals omega 2 minus 0 divided by 8. So from here, omega 2 is going to be equal 0.48 radian per second. Right? We have to just multiply those. All right, so that means that the carousel accelerates from omega 1 is 0 to omega 2.48 radians per second. Now for part B, the linear velocity is, as we said, v equals r omega. So we simply have to multiply 2.5 meters times 0.48 radians per second. And that is going to give us 1.2 meters per second. So notice how once you multiply meters times radians, the radians kind of disappear because it's just like, it's basically unitless notation. We're just saying that, okay, we're rotating with this speed, radian per second. It's, yeah, it's kind of like it's dimensionless. It's kind of just like a reminder for us. So that's that. Next problem looks like this. We have angular and linear acceleration. Same carousel here, same merry-go-round. We're going to determine the child's tangential acceleration, which is linear acceleration, centripetal acceleration, and then total acceleration. So we're using our equation 5. We know the tangential acceleration is r times alpha. So we have to multiply 2.5 meters times 0.06 radians per second squared. Again, that's just like a placeholder. And then we have 0.15 meters per second squared. Ta-da! Part A is done. Part A. Okay, part B. Now we are looking for the centripetal acceleration, AR, we know is equal v squared over r. I believe we found v squared to be 1.2 meters per second. We square that value and then we divide it by 2.5 meters. So once we simplify, we will get 0.58 meters per second squared. All right, and then finally, the total acceleration. Now let's take a look at the diagram here. So the total acceleration is going to be the sum. Remember, it's the sum of centripetal and tangential. And centripetal is directed towards the center. Tangential is tangent. We remember from geometry that the angle between those has to be 90 degrees, which means that we can use Pythagorean theorem to figure out the total acceleration. Part C, that looks like an O. It's supposed to be C. Part C. So using Pythagorean theorem, we will have to say that A has to be the square root of our tangential acceleration squared plus centripetal acceleration squared. And then now we plug in the values that we just calculated, 0.15 squared plus 0.58 squared. Once we calculate the square root of that, we are going to get 0.60 meters per second squared. So that means that the total acceleration is 0.6 meters per second squared. So you can see that all of those have different values. We can also think about we can figure out the direction of linear acceleration, and that is going to be determined by the angle theta. From the diagram, we can see that it will have to be the tangent of our tangential acceleration over radial acceleration, right? So that's our angle theta. We can see it here. So angle theta is going to be tangent, not that we had to find it, just for fun, tangential over AR. So that is going to be tangent inverse of 0.15 over 0.58 meters per second squared. They will cancel. So we will end up with 0.25 radians. So look at this. We also found an angle of the rotation, so which is about 15 degrees, approximately 15 degrees. Okay, one last thing that we need to discuss is frequency. So remember how when we talked about the circular motion, we described the frequency was 1 over time. So very similarly, here we can say the frequency, well, we will see how they're related. So frequency is going to be our angular velocity over 2 pi. So it's one revolution, right? So one revolution is going to be, you have to divide the whole path. You have to divide the whole velocity by the whole path, which is going to be 2 pi. All right, so that also means that the angular velocity omega is can be written down as 2 pi f, and we can say that those are equations number 7. The units here, we can say 1 revolution per second, but usually we use 1 hertz, just like the car rental. Okay, 1 hertz, named after a person, last name Hertz, physician. All right, so 1 hertz, capital Hz, is the same as 1 revolution per second. So again, revolution is not kind of like, it's not really a unit, kind of like the radians, it's kind of like a placeholder. So we can sometimes we can say that 1 hertz equals 1 second inverse, or second to the negative 1. And the time that is required for one complete revolution is called the period. And the period t is equal 1 over f, just like what we had for the circular motion. And that's going to be my equation number 8. All right, so that means that if a particle rotates at a frequency, let's say, of 3 revolutions per second, that means that the period is going to be 1 over third. Okay, and vice versa. If the period is 3, then the frequency is 1 over third, over 3, 1 over 3. They're reciprocals of each other. That's it for this lesson. Stay tuned for the next one. It is going to be about constant angular acceleration. Bye.